You look at a glycol gas dehydration unit and it appears simple. Wet gas enters, triethylene glycol absorbs water, rich glycol goes to regeneration, lean glycol returns to the contactor, and dry gas leaves the package. That sequence is simple enough to explain in a few seconds, but the real engineering is hidden inside the interfaces, assumptions, operating limits, and failure pathways that sit behind that process flow. I want you to understand one principle before anything else. You are not designing a contactor, a reboiler, a flash separator, a heat exchanger, and a pump as separate items. You are designing one connected dehydration system. Every weakness upstream eventually reappears downstream as poor dew point, unstable operation, foaming, glycol carryover, high fuel consumption, corrosion, fouling, pump problems, or premature equipment failure. This is where many designs go wrong. The package looks complete, the vessels are code compliant, the skid is fabricated, the hydro test is passed, the instruments are installed, and everyone assumes the job is finished. Then the unit reaches the field and starts consuming glycol, missing water content targets, foaming unpredictably, overheating the reboiler, or struggling at turndown. At that point, the same question always returns: what did the design miss? The answer is usually not one dramatic error. It is usually a chain of small assumptions that were never challenged. I would never begin a glycol dehydration design by asking what size contactor is required. I would begin by asking what gas actually enters the unit. What is the maximum gas rate? What is the minimum gas rate? What are the operating pressure and temperature ranges? Is the gas saturated with water? Can free water arrive? Can hydrocarbon condensate enter? Can compressor lubricant carry over? What concentrations of carbon dioxide and hydrogen sulfide are present? What outlet water content is really required? What turndown must the unit tolerate? What utilities are available? What happens during startup, shutdown, cold weather, upstream upset, and feed composition change? Those are not supporting questions. Those are the design. The correct net engineering chain is direct. Inlet gas conditions determine the entering water content. The required outlet specification determines how much water must be removed. The water removal duty determines the glycol circulation rate. The glycol rate, glycol purity, and required dew point depression determine the contacting requirement. Gas flow and allowable velocity determine the contactor diameter. Circulation rate determines pump capacity. Rich glycol loading affects flash separation, filtration, and regeneration duty. Regeneration duty determines reboiler size, fire tube area, and fuel demand. When you break that chain, you stop designing a process and start assembling equipment. The inlet scrubber is the first place where discipline matters. It is often treated as a routine separator, but it is one of the most important protective barriers in the whole system. The contactor is meant to remove water vapor from gas. It is not meant to accept uncontrolled free water, condensate, or compressor oil. Free water adds unnecessary load. Hydrocarbon condensate promotes foaming and contamination. Compressor oil can be even worse because it circulates with the glycol, degrades at elevated temperature, fouls heat transfer surfaces, and creates deposits. If you assume perfect upstream separation, the unit may look efficient on paper and unstable in reality. You should therefore ask whether the inlet scrubber can handle normal entrainment, upset carryover, cold condensation, upstream separator malfunction, and compressor oil contamination. Where oil carryover is credible, a basic mist pad may not be enough. More demanding coalescing separation may be justified. A design that works only when upstream equipment behaves perfectly is not a reliable design. Temperature is the next silent variable. When inlet gas is too cold, glycol becomes more viscous, tray efficiency can fall, pressure drop may increase, and carryover can worsen. When inlet gas is too hot, the gas contains more water vapor, so the dehydration duty rises. Higher temperature also demands purer lean glycol and increases glycol vaporization losses. This is why cooling must be placed and integrated correctly. If the gas needs cooling, the resulting liquids must be separated before the gas enters the contactor. Cooling without downstream separation simply creates free liquid and sends it into the absorption section. Inside the contactor, the real process is mass transfer. Gas rises while lean glycol flows downward. The two phases must contact each other effectively across trays or packing. The vessel may be mechanically sound, yet the dehydration performance can still be poor because the gas velocity is too high. The tray spacing is wrong, the packing is poorly distributed, the mist eliminator is inadequate, or the operating range is outside the hydraulic envelope. At high gas flow, you risk flooding, entrainment, and glycol carryover. At low gas flow, tray activity may collapse and mass transfer may weaken. This is why maximum capacity is only half the design. Minimum stable operation can be just as important. For packed contactors, more packing is not automatically better. Excessive height without redistribution create maldistribution and channeling. For trade towers, more trays do not solve every problem because additional trays also increase height, pressure drop, and mechanical complexity. The objective is enough effective contacting, not maximum internals. Lean glycol temperature is another critical control point. Cooler glycol improves water absorption, but glycol that is too cold relative to the gas can condense hydrocarbons inside the contactor. The useful design principle is to keep lean glycol moderately warmer than the gas, often within a controlled range above the gas temperature. The exact value depends on the service, but the principle is stable. You need enough cooling for efficient absorption without creating hydrocarbon condensation and contamination. This is where the gas-to-glycol heat exchanger matters. It uses dry outlet gas to cool the regenerated lean glycol before it re-enters the contactor. When this exchanger underperforms, the lean glycol enters too hot, absorption falls, and glycol losses may increase. A small loss in exchanger performance can quietly reduce the whole unit's capacity. Now let us address one of the most common operating reactions, increasing glycol circulation. More glycol is not automatically the answer. A typical system may circulate a few gallons of glycol for every pound of water were removed, but the correct rate depends on glycol purity, temperature, pressure, contacting stages, and required dew point depression. If the glycol is contaminated, insufficiently regenerated, or too hot, increasing circulation may simply increase pump load, heat duty, and fuel use without correcting the real problem. If the contactor is hydraulically limited, more glycol may make operation worse. If the mist eliminator is already challenged, extra circulation may increase carryover. So when dry gas quality deteriorates, do not immediately ask how much more glycol the pump can deliver. Ask what is actually limiting water removal. Is the lean glycol concentration too low? Is the glycol too hot? Are the trays active? Is the packing distributed correctly? Is foaming occurring? Is the inlet gas hotter or wetter than assumed? Is the reboiler performing? Is contamination present? Diagnosis must come before correction. The flash separator is another component that is often treated as optional because it is listed as optional. That is a dangerous interpretation. It is optional only when the service genuinely allows it to be optional. Rich glycol may contain dissolved gas and hydrocarbon liquid. A flash separator removes these before the glycol reaches the reboiler. Without that separation, hydrocarbons can enter the hot regeneration section where they may vaporize, degrade, foam, foul surfaces, and destabilize operation. The separator may also recover flash gas for fuel use. Where hydrocarbon contamination is credible, omitting the flash separator can save capital during procurement and create years of operating problems. Two-phase or three-phase separation must be selected according to what actually enters the rich glycol stream. Retention time must be based on separation difficulty, not only on minimum vessel size. The reboiler is where glycol is regenerated, but it is also where glycol can be destroyed. Water is boiled out of the rich glycol, but excessive temperature or local overheating causes degradation. Bulk glycol temperature must therefore be controlled, and the fire tube must be designed with sufficient area to avoid excessive heat flux. You should never review a reboiler only by checking total heat duty. The proper review includes fire tube surface area, heat flux, heat density, burner geometry, flame pattern, wall temperature, fouling tendency, fuel quality, stack draft, site elevation, and access for inspection. A reboiler can produce enough heat and still be badly designed. Excessive heat flux creates local overheating. Poor flame pattern creates hot spots. Deposits on the fire tube reduce heat transfer and drive wall temperature higher. Low glycol level exposes the fire tube. Weak combustion control wastes fuel and increases risk. A removable fire tube is not a convenience, it is part of maintainability. The still column also deserves more attention than it normally receives. It is not just a vent stack, it is a separation device that allows water vapor to leave while limiting glycol loss. Packing and reflux improve separation, but the overhead route must remain unrestricted. A small restriction in the still vent can create back pressure, disturb regeneration, and push the reboiler away from its intended operating condition. Undersized piping, liquid pockets, unnecessary valves, or poor downstream routing can all become major operating problems. A low-pressure system can still be a high-consequence system. Stripping gas may be used to increase lean glycol purity where ordinary regeneration cannot achieve the required concentration. That can be technically sound, but stripping gas should not be used to hide an undersized reboiler, contaminated glycol, poor contactor performance, or inadequate heat recovery. Use it because the specification requires higher purity, not because the rest of the system is underperforming. The glycol-to-glycol heat exchanger performs two essential duties. It preheats rich glycol before regeneration, reducing reboiler duty, and cools hot lean glycol before it reaches the pump and contactor. If the exchanger fouls, bypasses internally, or operates with poor temperature approach, fuel demand rises and lean glycol enters the absorber too hot. This is a good example of system interaction. One exchanger affects energy efficiency, pump conditions, and absorption performance at the same time. The surge tank is another source of hidden assumptions. It provides operating inventory and pump suction head, but it should not automatically be assumed to contain all glycol that drains back during shutdown. If the contactor and elevated piping drain into the surge tank, that volume must be calculated deliberately. Otherwise, the first shutdown may produce overflow, inventory loss, and a restart problem that nobody anticipated. Pump suction design is equally unforgiving. The suction line should be short, direct, and large enough to maintain stable flow. Avoid unnecessary elbows. Use reducers correctly so gas pockets do not form. Provide isolation and straining. For reciprocating pumps, review pulsation and line velocities. Many so-called pump failures are not pump failures. They are suction system failures. Replacing the pump repeatedly will not correct poor static head, gas accumulation, excessive friction, or a dirty strainer. Filtration must also be treated as process protection, not housekeeping. Particle filters remove solids that damage pumps and foul heat transfer surfaces. Carbon filtration may remove hydrocarbons and degradation products that promote foaming. A filter that cannot be isolated, monitored, or replaced easily will eventually be bypassed. Once it is bypassed, the contamination problem spreads through the entire glycol loop. Design the filter for clean and dirty pressure drop, element access, bypass philosophy, differential pressure indication, and realistic maintenance. Foaming is usually a symptom, not a root cause. It may be caused by condensate, compressor oil, solids, corrosion products, or degraded glycol. Antifoam may suppress symptoms, but permanent dependence on antifoam often means the source of contamination has not been removed. The correct response is to review inlet separation, glycol quality, pH, filtration, hydrocarbon loading, and regeneration conditions. Treat the cause before the chemical response becomes the operating philosophy. Glycol loss is one of the best indicators of unit health. High loss may come from excessive gas velocity, poor mist elimination, foaming, high temperature, still column losses, leakage, or excessive circulation. Do not keep adding glycol and call it normal consumption. Measure it, trend it, and correlate it with gas rate, inlet temperature, foaming events, separator performance, and maintenance history. Corrosion must also be examined by environment, not by generic material selection. Wet inlet gas, rich glycol, lean glycol, reboiler liquid, and still overheads are not the same service. Carbon dioxide, hydrogen sulfide, oxygen, water, salts, acidity, temperature, and deposits all change corrosion behavior. Rich glycol can become aggressive when acidity rises, oxygen enters, or degradation products accumulate. Still overheads can be highly corrosive where acidic vapors condense. Hydrogen sulfide introduces the additional risk of sulfide stress cracking. This is why material selection, welding, heat treatment, coatings, corrosion allowance, monitoring, and glycol quality control must be connected through one corrosion philosophy. Pressure relief responsibility must be explicit. Never allow the vendor to assume the purchaser supplies relief devices while the purchaser assumes they are included. Define who sizes, supplies, installs, certifies, and maintains each relief device. Confirm the relieving scenarios and confirm that the discharge route does not undermine the device's capacity. Instrumentation must also protect the process, not merely display it. Pressure, temperature, level, and differential pressure should support operation, while high-temperature shutdown, flame failure protection, low-level protection, and other safeguards should address credible rapid failures. A gauge is information. A trip is protection. Do not confuse the two. Startup and shutdown must be designed operating conditions. Before startup, the glycol inventory must be established, the pump suction must be flooded, filters must be clean, instruments must be checked, burner safeguards must be proven, and the system must be lined up correctly. During shutdown, drainage, trapped liquids, thermal expansion, and surge volume must be understood. When startup or shutdown repeatedly causes problems, do not automatically blame the operator. Ask whether the process design gave the operator a stable sequence to follow. The final lesson is broader than glycol dehydration. Equipment rarely fails in isolation. Systems fail at interfaces. The inlet scrubber affects the contactor. The contactor affects regeneration load. The glycol quality affects corrosion and foaming. The heat exchanger affects energy use and absorption. The pump suction affects circulation. The still vent affects regeneration. The surge tank affects shutdown. Instrumentation affects whether abnormal conditions become damage. A good engineer checks whether every item meets the specification. A strong engineer checks whether every item works together. A great engineer asks what happens when one item stops working as intended. That is where reliability begins. Look again at the glycol dehydration unit and ask yourself the harder questions. Can it handle the real operating envelope? Can it tolerate feed variation? Can it survive contamination? Can it run at turndown? Can it be maintained safely? Can it shut down without losing glycol? Can the operators diagnose what is happening? Can the system recover when one protection layer weakens? A compliant package is not automatically a reliable process system. Understand the process, challenge the assumptions, design the interfaces, protect against realistic failures, make responsibilities explicit, and never allow a clean process flow diagram to hide a weak engineering basis. Share your own experience in the comments. Which problem has caused the most trouble in your glycol dehydration systems? Poor dry gas dew point, foaming, glycol losses, reboiler fouling, pump instability, corrosion, bad separation, or incorrect design assumptions. Your field experience may prevent somebody else from repeating the same failure. Like this episode, share it with engineers who work in process design, mechanical engineering, instrumentation, operations, maintenance, and project execution, and subscribe to the channel for more direct engineering design and management discussions. Follow my LinkedIn newsletter for deeper articles on engineering standards, design reviews, failure prevention, project execution, and practical engineering judgment. Get in touch when you want to explore these subjects further, challenge an existing design, or turn field experience into better engineering decisions.